right. So again, a fish finder sends a sound wave at 75,000 hertz, reflects off a fish, and it's detected 0.071 seconds after it left the transmitter. The speed of the wave was 1,500 meters per second. Calculate the wavelength. How long did it take the wave to reach the fish, and how deep is the fish? So, I know, I just want that one to open. So let's do this. Okay. So, we have a boat. That's a boat. You're welcome. It sends out a sound wave and it hits a fish. Okay? At that point, the sound wave is reflected back to the transmitter and the boat reads that number. Okay? So the frequency, 75,000. This entire time, 0.071, and the velocity of the wave is 1500 meters per second. All right, part A, just want you to find that wavelength. I'm going to go velocity is equal to frequency times wavelength. Remember that lambda is wavelength. Okay, so we're going to divide. So being 1500 divided by 75,000. So that your wavelength is 0.02 meters. Pretty easy, right? Any questions about this part first? No. Okay. B, ask for the time it takes for the wavelength to get to the fish. This is a reflection of the wave. From here to here is a different time than the entire time. This is echolocation for a bat. This is Doppler. Okay, we use this quite a few times. So, to find the time to my fish, I would go 0.071 divided by 2. Why? Because it's half. Because half of the time is spent getting to the fish, the other half of the time is spent getting back to the boat. So that my time, in this case, is 0.0355 seconds. Don't forget, we are looking at a reflection of a wave, so you have to see where they want your data point from. C wants to know the distance to the fish. I found the fish. I want to eat the fish. I have to get the distance to the fish. I got to throw the net, the pole, the spear, whatever I'm catching the fish with. I got to get that there. So this formula is from the first 6 weeks. Velocity equals distance over time. I'm going to solve for distance because I want distance. That means my distance is equal to my velocity times my time. I multiplied both sides by time to get it across the equal sign so I could have distance by itself. Then I can just plug it in. Distance is equal to my velocity is 1500 times my time of 0.0355. What is the distance from the boat to the fish? Very good. 53.3 meters with some rounding. This is all based off that reflection of a wave.
So why did you divide the time by 2?
I divided the time by 2 because the time was picked up from when it sent this wave to when it got the wave back. But I only want the time to the fish. Any other questions over this? All right, we're gonna take like adult notes today. No. What? Me too. All right. So we are gonna basically just go over the things that you should have learned with the sub, and then I'm gonna introduce 2 new things. Be okay. Some of these terms, guys, should not have been the first time you heard them in here. They should have started in like 5th grade, maybe 6th. So, wave behaviors. The first one. Reflection. What is reflection? Bounces back. What? I mean, it depends on how you write. You should be good, right? I mean, make it work. Reflections when a wave hits a hard surface and bounces off.
Is it like our sound waves hitting the wall?
Yes. That's the sound waves hitting the wall. That is a bat echolocation. That is our fish finder. That is an ultrasound. We use this quite a bit. This is how we can see the cloud movements with the weather forecasting. It's just sound waves. So my wave's coming towards a hard boundary, hits it, bounces back up. And how it's transmitted is going to determine if it bounces back up to the transmitter or if it bounces off at an angle. That's just going to depend on the location of the source. Yes.
So I'm taking a walk with my grandmother. We're walking our dogs. She's behind me. And I say something to her, but I'm facing the front. And she can still hear it. How does that work?
Your sound is bouncing off of other things and coming back towards her.
But I'm in like the middle of the street. Is it that
There's
far?
still things. You're never just out there on your own. There's still
That's not bad.
cars. There's still light poles. There's still wind. It's not gonna.
There's just a lot of factors.
Huh?
There's a lot of factors.
Yes.
Lots of factors.
The floor
The floor.
that you're walking.
All right. Refraction's the next one. What is refraction?
Where it's I remember. I think where it's like we stick something in the water.
Yes.
And it's like
It's spitting. Yeah, that's it. That's just write that definition. Spitting. How do you spell that?
I don't think it matters. Yeah, I think it sounds the same.
This is image distortion from changing mediums. Pudding. So it's where your straw looks bent because it enters the water. So the light wave that you're looking at and interpreting hits the water, changes speed, and it looks like the straw is bent. This is why spearfishing is so hard, because the fish is not where you see it. If you've ever been like frog gigging, where you go and catch the frogs, you can't aim directly at that frog. You have to aim off from that frog. And experience will teach you which direction and how to make sure that you get that frog. The next one's going to be diffraction.
Is that where it like splits?
It's when it bends around something. The most common one you're going to see is when there's a hole in the wall and a wave is approaching. As it leaves the wall, its shape changes because it went through that hole. This is why you shouldn't talk about people near corners, because the wave will bend around the corner. Okay. Don't talk smack about people around corners, because the sound waves will bend around the corner. Someone might hear. Yes?
Aren't there also like really neat design qualities that like when you're at the end of it and you talk to move closer?
Yes, 100%.
Well, like what is that? I forget what it's called. They're built specifically for that.
For diffraction. Yeah. Those are creepy.
It looks like a face on the side. The big brow.
Absorption. Absorption. This is when a surface does not let a wave pass. Okay, the absorption of things change, like waves, is going to be different. So we have curtains to block out sound. We build big walls. If you have a neighborhood that's by a freeway, a lot of times your neighborhood will pay to put up a big wall there that's going to absorb the freeway traffic, because no one actually wants to live by that. If you're talking even something like nuclear waves, like gamma rays, beta rays, alpha, different things like alpha, I think, is stopped by paper. Beta is stopped by like a piece of foil will stop it. Gamma has to be behind the lead wall. So different waves can be absorbed by different things. All right. Echolocation is just reflection. So interference is our new term. It's when waves interact.
Like over the radio?
It can be. Yes, interference happens a lot when you listen to radio and like this plane or a storm. You have two basic types.
What if you hear alien noises in your car? Is that interference?
What's an alien noise sound like?
Yep. I don't know. It's driving and it made alien noise.
And you could just identify it as an alien noise.
It's alien to him.
Everything outside, yeah.
It's
It
foreign.
made weird noise.
You probably did have some interference. Again, radio waves can have interference from a lot of different things. Yes, Haley, we don't want to put a name to them, right? We don't want them to hear us. Yeah, the creatures in the sky.
Birds?
I'll name him Brother Bobo.
All right, so the first type of interference that we're going to talk about is destructive interference. So, if you've ever had like a 3-year-old little brother, they seem to sometimes choose waves interact. Yeah. It's a type of interference, yes. Destructive interference. So, take like a 3-year-old. Boys especially, they just tend to wake up and choose violence. And if you have like Legos and you have a $500 R2-D2 on the shelf that you thought was out of your 3-year-old's reach, what's going to happen? Yes. Right?
What about?
All the pieces, R2-D2 could not be put back together again. He was basically Humpty Dumpty, right? He was destroyed. He was broken down. Destructive interference.
On your bookshelf.
There is a spaceship on my bookshelf. Have you been to my house? You're getting a little weird.
There was one over there, but somebody just happened to knock it off.
Did you ever fix that one?
It's in the closet.
I would be surprised if you could have a spaceship on your bookshelf.
All right. So destructive interference happens a lot when two waves meet and like they're out of sync with one another. Their crests and their troughs are just gonna collide, and what you end up with is a wave with less amplitude. Remember that amplitude's at height, there's a depth that the wave achieves. So in this case, we took two normal size waves, and when they met, the resultant wave was less. You can think of it as, chances are if two people jumped in the pool, opposite ends cannonballed in, their wave is going to meet in the middle, going to kind of cancel each other out and not be as much. The other one is constructive interference. So construction crews typically build buildings up, right? So a constructive interference is going to make a bigger wave. So whoop, plus whoop, equals one with higher amplitude. There was just a world record set sometime very recently. Some guy was like 1,500 foot wave or something that he surfed. Like, it's huge, terrifying. Like, I thought it was a tsunami coming, but he was surfing it. It was a video. It was video editing, absolutely. But those creatures in the sky messing with your radio, those.
Every single thing.
It was something.
It was definitely. All right, resonance is when an object vibrates at its natural frequency. Okay, this is what happens when you see those opera singers and they sing at such a loud, intensive voice that it breaks a glass. That's resonancy. We typically see resonancy with a tuning fork, which I'm going to show you here in a second. Resonance is when an object vibrates at its natural frequency. If the opera singer can get to that glass is natural resonance, the glass can vibrate, and because it's held in a certain crystalline structure, it can shatter because the vibrations become too much. What? I don't have it. Yes. Okay.
Just like part intel, when you talk, cut out from the brain.
When militaries used to march a lot, like to go on military campaigns and stuff, generals always told their soldiers to stop staying on beat when they would cross a bridge. They didn't want to hit the same beat on the bridge and potentially have it collapse because of the vibrations. That's resonance. Really, really bad if your whole entire crew is going across and it just whoop.